已解锁形体通话筒。
雨太大。啊？怎么是这么点？对啊，雨太大了。 也这样你就先开始吧。今天的雨下很大，嗯，今天雨下得很大，我也不想来上课。看到我整身都湿了，我背也湿。然后今天的 printer 还不能用，今天真的是糟糕的一天。printer 打印机糟糕的，看一下下完能不能用。Okay, let's continue with 什么？整天再见。Exact sequence and excision. Okay. Excision is like a Caesar method, so it's like you take away something. Okay, so we'll discuss introduce what is excision. So what's the motivation for this part here is maybe you want to ask a question, what is the homology of quotient space? Okay, so what's the homology of quotient space? So as a mathematician, right, or mathematics student, right, you like to have a homology that respect this quotient. Okay, something makes sense to us here. So, hey, hello. 你现在会大吗？还是很大？Okay. So, uh, yeah. So, do we want this to be true always? Actually, if this is true, then take, for example, x to be a. Okay, what do you get? So on one side, you get the homology of a point. The homology of a point last time, if you still remember, when n equals 0, it is z, right? But on the other side, we have hn over hna over hn a, which is 0. But when n equals 0, here 0 of a point is z. Okay, so you have a contradicting homology theory if this is true. So this cannot be true. If it's true, then we don't need to have this subject anymore. Okay, so this is not true actually. Okay, so this is not true in general, but there's something to relate between three of these things. Okay? But there's this relation between three of them. Okay. Yeah. Any questions so far? Yeah. Yeah. You make it to a single point. And then zero homology of a single point is Z. Okay. Yeah, so in this case, then I will define something called the exact sequence. So let's say a sequence of homomorphism. So this is following the homology pattern, descending order. If this alpha n is said to be exact, if the kernel of alpha n is equals to the image of alpha dn plus. Okay. Okay, so to be a chain complex, you always have one direction to be true, which is image of alpha n plus 1 is the kernel of alpha n. This is guaranteed by alpha n on alpha n plus 1 is 0. This is about chain complex. But if it's exact, then we have the other direction. Okay, if it's exact, we have the other direction. So the kernel of alpha n is in the image of alpha n. So it's realized by the previous step. Then we'll call it exact. Or sometimes we'll say that it's exact at a certain point at n. Okay, if this is true. Okay, so we have a bunch of kind of obvious proposition coming out from this exact sequence here. So we say that this sequence from 0 to R to A to B is exact if and only if the kernel alpha is 0. Okay, so meaning alpha is injective. Okay, so if it is exact means what? Kernel of alpha is equals to an image of a zero map. So kernel of alpha is 0, kernel is 0, meaning the homomorphism is injective. If the homomorphism is injective, meaning the kernel have to be 0. So this is kind of obvious. So next, we also have another exact sequence looking like this. Yeah? Huh? Have to be to 0. What do you mean? Huh? Go to my right. So, yeah. So injective, you just need a 0 on the left hand side. But surjective, you need a 0 on your right hand side. Why? Because if you have this to be exact, okay, if you have this to be exact, this means what? The kernel of a 0 map is the image of alpha. So the kernel of a 0 map is equal to the image of alpha. Meaning what? So the kernel is equal to this image. But what is this kernel? This kernel is a 0 map, kernel of a 0 map. So everything gets sent to 0. But everything is an image of alpha. Okay, so it's injective because everything mapped to you. And you are the kernel of 0 map. Okay, so 0 map is very interesting here. So if you have 0 going to A, just means that you include 0 in. If you have a map into 0, that means everything gets sent to 0. And so this is the thing you need to know. As alpha is surjective. How about if we put these two exact sequence together? Okay, so meaning you have two non-zero position squeezed by 2 0 here. And then we say that this is exact. What happened? This means that alpha is injective and surjective at the same time. So meaning what? If this is exact, then alpha is an isomorphism. Okay, so previously we were right like this, right like this. Okay, so now you can replace it as a chain complex. Okay, next. 0 to A to B to C. Okay, so if this is exact, what will happen? So from previously, we'll know that alpha is injective. Okay, and then beta is surjective. And then what else can we know about it? Here, there's the third place to be exact, right? And at the same time, kernel of beta will be equal to the image of alpha. Okay, so now you got a surjective map from B to C, right? And then you know the kernel. And then you know the kernel. Okay, so this by first isomorphism theorem, we know that B mod out by kernel B is C. But at the same time, we know that kernel B is actually the image of alpha. Okay, so actually we have beta, where B quotient out by image of alpha is equal to C. But What do we know about image of alpha? A is injective. Yes, so actually there's an isomorphism between image of A and A. Okay, so in the end, what we get is C is isomorphic to B over A. If we have this chain here. Okay, so meaning if you have something like B over A, you can replace this with a chain complex as well. Okay, so how do you see this chain complex is you have a map, surjective map from B to B to C, and then there's a kernel mapping into. Okay, so we record this portion using a chain complex. Okay, so if you use this logic, what happened here is in this isomorphism here, you have a surjective map, but there's no kernel. Okay, so that's why it ends with a 0. So it gets shortened. Okay, makes sense so far? Makes sense? Okay, so there's some terminology maybe I want to introduce to you. So we will define that B mod image of alpha is the co-kernel of alpha. Okay. So maybe I draw a picture to you. So here you got the A. Here you got the B. Right. So if your kernel, right? So what's your kernel? Your kernel is something gets sent to 0. Okay, so here is kernel. But what's co-kernel? So co-kernel is you map A to something, image of A, and then other than these, other than these are the co-kernel. Okay, so it's like a counterpart for your kernel. Counterpart for your kernel is B. So these are the co-kernel of alpha. So our map is alpha. So image of kernel alpha. So kernel alpha is in A, but co-kernel alpha is in B. It's not. Huh? Co-kernel is in B. Yeah. Co-kernel is in B. Huh? Uh, oh yeah, sure. Okay, sure. Yeah, so you should understand this co-kernel as a equivalent class. Yeah. You identify those elements in image of alpha. Okay. So then this is what we call a short exact sequence. So an exact sequence from A to B to C squeezed by 2, 0 is called an short exact sequence. Okay, so short exact sequence will give you the information of C. C is isomorphic to B over A. Okay, so in this case, C is isomorphic to B over A. Okay, because there's an injective, there's an surjection from B to C, and then an injection from A. We'll abbreviate it to be a SES, short exact sequence. Okay, so far any question about this exactness here? Okay, so I provide another way for you to write isomorphism. Yeah, to write isomorphism. Hey, hello. Hello. 叫泰语啊？睡过头了。你为什么早上没有继续跑？你们应该可以自己跑的。我本来没有忘记跟你们讲去，通常礼拜天晚上会先讲。然后我以为你们没有问，所以我以为你们也没有 想跑，所以忽然间早上看到 message，吓到我。跟紧，下次我们会 organize 一下。Okay, right. So yeah, we have talking about shared access sequence just now. So shared access sequence is a sequence such that the kernel of alpha n is equals to image of alpha n plus 1. So meaning the kernel of the map is equals to image of the previous map. Okay? We only have one inclusion if you are chain complex, but the other inclusion will be given by this exactness. And these exactness have a nice way to help you to describe something is injective, surjective, or isomorphism, or quotient, or in terms of quotient. Okay, I think the most general. So if you have an exact sequence, this is called short exact sequence, so which is 3 terms, 3 non-zero terms, squeezed by 2 zero here. This is exact. Then C will be isomorphic to B over A. Okay, because you can trace to the exact location. Where you can trace to the exact. And because if you have a surjective map from B to C, then by first isomorphism, B over kernel, the map is C. But because we have exactness, we can bring this kernel to the image of the previous map. And then because this image here is injective, this map is injective, it's just the domain isomorphic to domain. So we will get C isomorphic to B over A. Okay, so this is the one way to record a quotient module, whatever. Okay. Any questions so far? No. Okay. So this is the most general one because if you imagine that B and C is the same, then this kernel will be 0. So that's why we got the part 3 here. Okay, it's the shortened one. The kernel part becomes 0. So become 2 terms inside of exact chain complexity. Okay, so far so good. Okay, then we will have next proposition which we won't prove yet. We will prove a more general version. Let's take it first, following the actual pattern. Where is it? Okay, here. So let's state it. We won't prove it. We'll prove a more general version. So if X is a topology space, A is a non-empty closed subspace that is a deformation retract of some neighborhood in X. So this picture you should think like you have a X here, then you have a A here maybe. Okay, it's a deformation retract of some open neighborhood, or maybe something like this. Okay, that can be deformation retract from some open neighborhood, then that exists a long exact sequence here. Okay, or sometimes we call it LES, a long exact sequence. Sometimes we call it LES. So long exact sequences, look at how they arrange it. HNA to HNX. Okay, this is still following the induced homomorphism for the inclusion. And then J is coming from the quotient X to X mod A. Okay, but the point here is you can connect to the lower homology group. And this method repeats. Okay, AX X over A and then AX A over A and then AX A over A. But you can go down a level of homology. Okay, so I mean this inducement should be obvious, right? Because last time we had inducement on chain complex and then induce on homology. But this connecting map here is not obvious. And later we will prove it using technique what we call diagram chasing. You need to chase the diagram. Okay. And you should think about how to relate the chain group of X over A to C minus 1 chain group. Y can go down. Yeah, so if we have n at every level, right, meaning you also have chain complex for A for X over A. What do you mean? Yeah. So for each, so you should imagine that for each of them, there's a chain complex. And then because we already have map in between A, X, and X over A, then you can reduce them to a map of chain. And then you need to check this one. Okay, so it's kind of like a ladder. It's like a ladder. So CNA, CNX, and then CN X over A, and then Cn minus 1 A, and then C plus 1 A, like that. Okay, so it's like a ladder. Yeah. Okay, so you should think of it like, how can you map something in Cn of X over A to Cn minus 1? Okay, how do you bring this element down? So, I mean, like, one way to bring down to here is you can use surjective first, right? You can use surjective first and then map it down. But this map it down, then you need to describe how can you map it to something here. How does it make sense to map to something? So this is surjective, so you can bring it here, but you can map it down also. Okay. Yeah. Then you need to think why I can put it to Cn minus 1. But later we'll try and do this together. Okay, for now you can think about it. Okay. In this case here, since this happens, right? So we'll call this kind of X and A, right? A good pair. Okay, they are the good pair. Huh? 什么 better pair？ 这样子没有。Good pair， 他们是好队友。啊？坏队友？Why？ Why？ 哦，没有，不是 good 就是 bad 了，不是 good 就 bad 啊，没有特地讲 bad 了。If it's not good, then it's bad. So far, there's nothing for bad pair yet. Okay, so this is a good pair. Again, good pair will give you from a short exact sequence to a long exact sequence. Okay. Right. So maybe we can quickly prove something using this theorem and good pair before we even proving the theorem yet, because we'll go to a more general setting later. Okay, so now we're going to prove that the reduced homology of Xn is Z, and reduced homology of Xn, reduced homology of Xn at degree n is Z, and then at other degree is 0. Okay, so maybe you can ask a question why the degree 0 is not Z? Because degree 0 is about half connected, right? Xn should be half connected, and there's only one connected component. Okay, because we are considering the reduced case. Okay, if it is reduced, the degree 0 already become 0. Okay, for one half connected part, but there's only one half connected part for component for Xn. Okay, so how do we prove this? So we're going to use the theorem we had just now. We need to produce a good pair. Okay, we're going to produce a good pair. Okay, so what's the good pair we're going to introduce here? Well, so this n hole, okay, let's start for n greater than 0 first, and then we can discuss what's n equals 0. Or you want to discuss n equals 0 first? Are you happy if we start n greater than 0, and then later we discuss n equals 0? Okay, good. Okay, so let's discuss greater than 0 first. Then later we discuss n equals 0, what happened. So for n greater than 0, what we can take for good pair is Dn and Sn minus 1. Everyone okay with Dn with Xn minus 1? I think in the exam, someone confused a little bit. They take the Sn greater their Rn. So actually, your Sn should live inside your Rn. Oh, see. So Dn may be like this, and then Sn minus 1 is inside here. Because Sn minus 1 live in Rn. Dn live in Rn. So this is the case of n equals to 2. Okay, like this. Okay, if you try to attempt and draw S2 here, then you are a bit confused already. Then you go up a level higher. Okay, so is it clear that this is a good pair? There is a neighborhood deformation to Sn S1, right? Because the neighborhood could look like something like this. We're looking like this. So deformation retracting Sn S1. Okay, so if I take this quotient, right, the claim here, this is Sn. Yeah, is it true or not? Right? Yeah, definitely. Wait. Why can't I see it? So let me think. Wait, let me see. It's a different version of contract. Yeah, wait. So are you saying that where? So it's a different subspace, it's a deformation between of some open neighborhood in X, which could pair. Oh, well, good. So this Sn minus 1, right, actually, I don't simply pick it. Actually, I should pick the boundary. Yeah, I should pick this one as my Sn minus S1. Okay, I should pick this one. I pick the middle one, seems like a bit stupid. Okay, I should pick the boundary one as my S1. Okay, obviously, there's a neighborhood that retract to it because you can pick this. Because I don't know why. Because they are homeomorphic. They are homeomorphic. Okay, anyway. Okay. So now we have a good pairs, right? Meaning we have this long thing. Okay, so this long thing, can you remember or not? So it's just inclusion plus a quotient, and then you put all the level of reduced homology. So this one is just for reduced yet. Reduce. Okay, so we have this long chain here. Well, but there's a lot of term is zero because dn is contractible. And there's a lot of term inside there is zero. And so in particular, the HIDN is zero. Okay. So all the A here, the homology of A is zero. Okay, so there will be like 2 terms squeezed by 0. Wow, this is very good. Yes. Uh, this is contractible, right? So contractible become the point, right? Point only have non-zero homology at the 0 degree, but that's the point we introduce reduced homology because in the reduced homology, the point also get 0 at the 0 degree. Remember, H0x is isomorphic to H0x to that function because this part we're gonna be set. So H0 reduce degree 0 homology will be 0. Okay. For 1 point. Every spot is true. Yeah. Okay. Yeah. So your long access sequence will reduce to like 0, 2 times 0, 2 times 0. Yeah, but the 2 terms is what? So the 2 term is what? Actually, your non-zero term is here. Non-zero term is here. Hn and Hn minus 1. Wait, let me think. Yeah, I'm wrong just now, right? Because here is Sn minus 1, here is Dn, here is Sn. Okay, actually the thing that goes to zero is hash x. Reduce hash x. Okay, so you can see that squeezed by these two zero term was the hn term and the hn minus one term. And then exactly these are relating the two different Sn. The two different Sn. Okay, does it make sense? So they are isomorphic. They are isomorphic between Hn Sn and Hn minus one Sn minus one. So you have this isomorphic chain here. Does it make sense? So did I write it down? Yeah. So I have this. This is isomorphic. Okay, so this is also isomorphic to Hi minus 2 and then Sn minus Sn Sn minus 2 like that. Hi minus 2 and then Sn minus 2. Okay. And then this is true for let me see, this is true for all I. So you are true at the n level, you are true for all the I below. Let me see, it's correct. Yeah. Okay. Because if you fix an n, you have all the hi to be true, and then because your n can move also, you can move the n to different for Sn. Does it make sense? You know what I'm talking about? There's two index running here. One is n, one is I. I is for the homology. So there's two index. One is the index for x, and one is the index for hn. Two index. You fix an Sn, then you have all the hi. Okay. 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 So this is what happened here. Okay, you have this isomorphism. Okay. So what does this mean? This means that you only need to ask the question of what is hash, for example, I minus, what is I, what is this term here? Wait, let me see. So no, what is okay? Let me write down here. Let me write down. Okay. So we get hi Sn isomorphic to hi minus 1 Xn minus 1. 4. Okay, so you can go all the way back to H0 of S0. You have a question? 我想一下，我有问题吗？我问题在哪里？
You're right. H0 should be S.
Oh, wait, sorry. So I guess I think we only stop at xn, right? We stop here. For one n, we stop here. Okay, so let's bring this long exact sequence down. Oh, let's bring this down. Okay, let's look at this guy. We haven't proved it yet. We just try and use it. Okay, so the last part here is Sn. Okay, so we'll stop here. Okay, we'll stop here. Okay, so the question is, what is this? This is what? This is 0 because there's only one path connected component. Okay, and then this is for I not equals to n. This is for I not equals to n. Let's see, is it correct or not? Should we write down term by term? So, wait, let's think. Okay. Yeah. You mean for this guy here? So why is it 2 and 0? So let me write the previous term. So hash 0 of x of dn, which is tilde. Yeah, sure. Yeah. So this part is 0 as well. Okay. Yeah. And then how about the rest? This is for I is not equals to n, right? How about I equals to n? Okay, so if I equals to n, what happens here? Hash n of xn is isomorphic to, yep. 什么？这个啊，这个啊。Okay, let's see, is this good or not? Well, because I was thinking that, okay, how about let's try a few more terms down. So we should have hash n minus 2, hash n minus 1, sorry, of x over a, and then hash n minus n, 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 n minus 1, n minus 1, n minus 1, this one, n minus 2 in here. So we replace them. So x will become dn, and then x over a become xn, and then a become xn minus 1. Right. And then hash n x disappear, dn minus 1 disappear, this one disappear. And then we have isomorphism in between these two. 我想一下啊。对，我看一下。Let me see how to link this. Okay, even we don't care about I not equals to n, we also already know for all I this is true, right? Because these are squeezed by 2, 0 here. Okay. And then next, we're going to use this result here. Let me see how do we use this. Sn, right? Sn. Here is Sn.
No, you just use this chain, but after that, from this chain, you get this homomorphism, isomorphism. Then forget that chain, you just use induction on this.
Yes, yes, yes.
Because you have HISN isomorphism to HI minus 1 and minus 1. Then you use another chain to conclude HI minus 1 as N minus 1 is isomorphic to HI minus 2 as N minus 2. Then you just use induction. But when you use induction, actually you are using different chain to conclude this isomorphism.
So what chain I'm using?
Put Sn minus 1, replace Sn minus 1 and S minus N with Sn minus 2 as N minus 1.
You mean, well, let me think first. So, okay, so because we know that this is true, so we can like, this is isomorphic to hash I minus 2 of xn minus 2, is it? You just follow this change, this isomorphism here. You put a minus here, bottom at the top, 1 is at the top. But no matter how, we know that hash 0 of some Sm is 0. This is what you're saying, right? Okay, makes sense. Does this make sense so far? Okay. Then if this is for I not equals to n, right? Okay, above is true for, okay, so this is first, this claim is true for all I, but if I not equals to n, the bottom is true. But if I is equals to n, then what we get is hash n tilde Sn isomorphic to hash n minus 1 tilde xn minus 1, and then blah 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 will stop at hash 0 of n0. So we need to know what is this guy. Is this guy 0 or not? Huh? Hash not tilde of s naught is what is this? Okay, so how to compute this? Well, I think we need to use hash x naught isomorphic to hash naught x naught tilde plus z. Okay, so we need to ask what is hash naught of s naught. Okay, you can use chain complex because there are only 2 points here. So there's only 2 terms in your degree 0. So let's say this is u and v. Actually, one of them is 1 minus 1, one of them is u, right? One of them is 1 because it's a unique length one. So the C0 term is actually z of minus 1 and 1. Can I write like this? Because they are not z of, they are a point. So maybe call it u and v. Otherwise, they get mixed into a scalar. But there's no differential map here. There's only 2 points. Yeah, actually, hash naught of s naught is z2. So hash naught is z. And z2 equal to something times z plus z2 then plus z. So the thing here should be okay. Okay, so far okay or not? So for the long exact sequence, we will only get this this isomorphism here, and then we apply this isomorphism. Yeah, this is the story. Okay, so far so good. Induction proof plus a long exact sequence. Okay, so the idea, the moral here is the long exact sequence can help you to relate different degree of homology. Different degree of homology, and then this homology of Sn here. Okay, there's another fact you want to remember here is Sn only have reduced homology, non-zero reduced homology at the degree n. Okay, so this is a very nice space sphere. only at degree n reduced homology you have non-zero. Which is that? Non-zero group. At other place it's 0. So it's like 0, 0, 0, 0, z, 0, 0, 0, 0, 0. Right? You can think of it like a delta thingy also can. The delta function, right? So you meet n and then you got z and then the rest is 0. Alright, so this is nice thing about this field. Okay. Delta function. Huh? Dirac Kronecker delta. Yeah. Okay, one last thing before finish this part here. So boundary of Dn is not a retreat of Dn. This is something that we proved last time, isn't it? Hence, every map of Dn to Dn has a fixed point. This is another proof here. Okay, last time if you still remember, we drew a ray from Rx to the boundary, and then we try to assume there's a retraction. But then we will prove that the pi1 of xn is trivial, which is not true, contradiction. So now we will have another proof here using this long exact sequence. Suppose if it is a retraction, okay, from Dn to boundary Dn here, then together with this inclusion boundary Dn to Dn, we will have identity map with this composition. I think we are quite familiar with this, right? Because I got this. We include and then retrain. Last time was retrain include. No, retrain. Include and retrain, right? Include first and then retrain. Okay. But then what? But then the inclusion and retraction here must be 0. Why? Because hn minus 1 of dn is 0. Okay, so we have a contradiction. You cannot get identity map. Okay, so this is like I think like the assignment question. You have a circle and then you put into somewhere that's contractible, and then this circle disappear, and then you want to retract again, you cannot see the circle anymore. Okay, so I want to end this lecture, not like this lecture, this hour of lecture with a video. Have you guys seen it? I share in your group. 没有看过? Okay, 我看一下. And this part of lecture with this video here. 你们没有看人家 share 的话，你们可以注意看一下。有看吗？就你们。我的 group 到哪里去？Where's the group？ 大家哦，有一个mark with 3 hole， 我也是有 share， 你们可以看一看。可能有人要问哦，那课来干嘛？这课解释，大概解释。
thinking about it was because of this theme about what first one laid flat, the second one crumpled, but lay on top of
Raoul
it.
fixed point theorem.
There's only one point on the crumpled piece of paper that lies directly above the exact same corresponding point on the flat piece of paper. Like always. This is Raoul's fixed point theorem, which is like the key result in the mathematical field of topology. The reason why I was thinking about it was because of this theme about whenever I see shape, I'm like a loop and sort of a blob. I think of the famous mathematical statement that said topologists can't tell the difference between a coffee cup and a donut. Topology is often referred to as rubber sheet geometry, where shapes are classed as the same if they can deform into each other without any tearing happen. So real world applications. Brouwer's fixed point theorem helped prove a really key result in chaos theory and economics, which is Nash's equilibrium theorem. Yes, this is John Nash's theorem, the subject of the film A Beautiful Mind with Russell Crowe in it, which was the reason why I got into mathematics and loved mathematics in the first place. This says that in any game where players each have a set of strategies and their payoff depends on other people's choices, there is at least one combination of strategies where no player has an incentive to change their choice, i.e., there's a fixed point, there's an equilibrium. And this is super important as it formalizes how markets can reach a balance even when individuals are acting in their own self-interest.
Okay. So John Nash came from Topology. John Nash result. If you're interested, you should make it your project. All right, let's take a break until 10:07. Come on. Notification?哦，是诶，
不是这个，
啊，然后呢？
为什么我等于零？
没有，它会停在零的嘛，反正
没有，它停在
它会停在
这个只能通过这个，然后这个
这个 n 应该跟这个
这个
n 都没有关系。啊，
这个东西，这个等于零跟这个东西没关系，这个等于零是因为它最后一项是夹在两个零中间的，
你也可以那样子想，但是你也可以
或者 just as n is class connected。
啊，这个 n 跟这个 n 应该没有关系，这个是 random 的。
对，
人在你种还是零？
哦，每个人的 n 啊
因为
，n
每个
只要
n 我都能
n 只要大过零的话，就是 SE 那些嘛，那些你要如果你要正的话，你不要正，为什么只有一个 path connector component？如果你正了那个过后，then from 我们那个 reduce homology 的那个 path 你就知道 reduce homology of 一个 path 只有一个 path component 的 spacing。
S 零是两个吗？
啊 S 有两个，所以这个是 n 大于零的情况。这是 n 大于零的情况。
这一下会夹在两个。
但是 n 大于零的情况，n 等于零的情况是另外一串。
所以它这个 induction 才搞慢了。
让你能够从 h 零 of Sn 推到不同的 hi of Sn。
对，
这个
可是你这个 induction 还会变小哦，
这个 i 会变小，
因为你从零开始，然后
这个什么？
哦这个零，对 SE 啊，
没有，这个是 induct 在 i 上面，你要 fix 一个 n。
那还这样 induct 在 n 哦。
因为这个是当 i 等于 n 的时候，所以我刚才读的时候也是有点 confused。OK，我重新写一下它的。它是 i 等于 n 的时候，然后 induct 在 n 上面。它的这个派也写到怪怪嘛，它这个 n 其实是乱跑的，这个 n 是 fix 的。
对，
理由的 n 是乱跑的。
就是你塞一个 n 然后你就有这个东西吗？
对，我重新写一下这个派。
我怎么觉得好像佛发机的那个证明里面有点在用类似的思路？
都是类似的。
我知道那个 x 的是啥，那个是 derive from 12那个 home。
你这个礼拜是谁帮你的？
对不起啊，我 Homology 的一开始
礼拜这个礼拜会久啊，我哎，你们那个什么 study group 这位还没有破出来呢，一点怎么嘞？很奇怪耶，有人要来。哦，是 Rachel 啊，是 Rachel。没有哎，换了啊，没有啊，你把你提上去了，那个红瑞代替你了，然后 Rachel 了，然后就到小月了，小月就到2号天了，2号天就到 NJ 了，然后呢就要差不多要结束了，这些。
最後2週復資我哋說，等我 week 7收到我話你嘅，Homology 發到我咪好。
哎，红瑞我 lecture 14加了一个 slide，可能你要看一下最后一个 slide。我加了一个 part 是关于说 Pi1 和 H1 的，我没有加那个 proof 啦，可能那个 proof 可以打在 solution 里面，那 proof 在 H 里面，那 proof 很长，但是主要是我要有那个 isomorphism。还有那个 Larry，你的 homotopy type definition 没有打进去，你打了 homotopy equivalent 过后，下一个 statement 是关于 homotopy type contractible，然后怎么会漏掉？应该是我漏掉吧，maybe。你是拿旧的版本是吧？你 check 一下新的。哎，你们负责打那个 w e 不是常常 check 一下我有没有更新？因为有时候我在更新后面的时候，我一看到哎这个东西还在前面，应该就要介绍，但是没有介绍就补进去。
然后
哦，加一 chapter 对，
对，加了一个身份，然后那个 lecture 是 A 人打的，然后他们的一个身份加了一个 lecture 一个，然后觉得果然就是个火。
你知道什么情况吗？因为那个 mouse red 哦，他讲到那个 chapter 很简单啊，原来那个 chapter 是个大 chapter
不如咱挺难的呗。
是啊，整个 dimension 可以开一个课了，我感觉
不用，他讲
可以开半个 sem 的课了。
他讲简单是因为他那个
对啊，而且它 reference 那个是超难的东西，但是我发现到有比较简单的 treatment，但是毛帅就不想进入那个课题嘛，他就
感觉缺了几十个鬼东西，这是什么鬼？然后再 check，哦，是你加了几十个鬼，
对啊，
然后就开始整我一些。
因为毛帅是比较 geometry 的，他没有进到 algebra 里面，所以他就没有用那些 algebra 解释来解释 dimension，他就 cite 那种 geometry 的 proof。
哦，
确实啊，那个 dimension 是一个大课题的 dimension theory。
你看有吗？
看不懂。
不出来了，我还讲。
反正
我加进去的东西是比较偏 algebra，
对，
就叫 algebra 嘛。
Algebraic calculation dimension 整个东西哦，非常好像
它只是 algebra 吧，它就纯 algebra。
他讲说你刚才那个东西感觉不太就我们 A G 打出来的东西，感觉我们自己有把好点学习。
啊，
就那个 motivation 好像
尤其是后面几章，前面几章是好的。
我们一大堆 module extension
啊，对，extension 有一点点，对，我觉得以后可以让他们先拿 algebraic number theory 先。你有看他们三个 algebraic number theory 吗？你们？他们前面的 part 跟我们的 part 差不多重叠，其实 commutative algebra 那个 part，他们也是讨论那些 unique factorization domain 啊什么的。对啊，如果上了那个过后 ，AG 那个就可以推更前面一点，
那 A G 不至少得放也是。
是吧？
一个课本
对
它是个灵活嘛，
对，
有人问我就问我那个
目前
那个专 A P，
然后呢？
哦，然后他讲scheme 那种语言啊，是 classical。
，OK，
我以前
可能 idea 是 classical 吧，但是那个字肯定是 modern。
你讲我以前问的，
你看 Grothendieck 就是 modern 啊
弄
，scheme，那也可能，
我跟你讲他是 classical scheme
那也可能，
scheme，
他眼里是
那也可能，
然后还有讲现在我 AG 有
还有什么
有个
stack 啊那些，
stack 好像你再上两次才到。
不是一层吗？
然后上面好像是叫 algebra space，然后在上面就是 algebra stack。
是吗？OK，
affine space。对，反正上面有一个 space，然后在上面就是 stack。
OK，
我出点对吧？
好。
对啊， A 还是什么？把那个 A 去发给我，
对，其他可以，
你们打的 A
我没发你们，
不见了，
我没在电脑里，那个我的。
靠！怎么进掉耳朵？看他们的屁股。
Okay, to prove the general statement for the connecting homomorphism for long as a sequence, right? We'll do it now or next time, but we'll introduce the machinery now. This is called the relative homology group. Okay, so we really want something like a quotient, but how do we introduce this quotient? This is how. Okay, so let XA be a pair. Okay, this is just a pair, no need to be good pair yet. Okay, so a pair is just a subspace of each other, that's it. Not each other, one is a subspace of the other. Okay, so meaning the second one is a subspace of the first space. This is enough. Okay, this is a pair. Okay, good pair have a deformation property, deformation retrieval. And then we will view CNA, the co-chain that define A as a subgroup of CNX. Free abelian group, right? So it's a subgroup here. Okay, and then we define the new notation here. Please be aware, CNX comma A. Okay, previously we just had CNX. Now we have CNX comma A, which is CNX quotient by CNA. Okay, because we view CNA as a subgroup of CNX, so we can quotient it. For now, does it make sense? For now, CNA is some singular simplex. Okay. So you take away simplex that define on A, meaning what? You are killing the simplex that have value on A. Does it make sense? This relative chain here. Okay. Yeah. So you kill any chain, n chain at A. So that means your singular simplex doesn't have value on A. I mean value is 0. Okay. Okay, huh? Okay, so what's the boundary map here? How about boundary map? Actually, boundary map is the same. You just take CNA to the equivalent class of the boundary N of C. Okay, you just apply the previous boundary map. Is this confusing? Lydia, can I abuse notation here?
写出来啊！
什么好写的？A bit like restriction or the quotient map. Or you want me like this 呢？这个米有很多次出现了，还是用8就8了。如果你要的话，but 等你认识了，它就是 boundary n 嘛，因为它确实是 boundary n。Okay. So then you need to also prove that this form a chain complex. Okay. Yeah. So if you like, this boundary n really come from this kind of the original boundary map here. It's just that we apply the quotient So if you like, you should check. Actually, you should check. Rachel, you are doing this week. Actually, not. Maybe you can check why I can induce a boundary map here. Okay, yeah. Why induce the boundary map? Should be okay, right? Should be okay, right? Because if you write as a concept, you are just writing it as something is here plus something in here, right? And then if you add the boundary, because boundary map is homomorphism, so you have to add on both parts. But you do twice, you also do twice on both parts. But this is a boundary map, so both parts have to go to 0. So this induced one is a trend boundary map. Okay, then we'll define the relative and relative homology group. And relative homology group, which is hash n of x comma a, which is the hash n of this chain complex here. C blah. And then the element here is called a relative cycle. Boundary is called a relative boundary. Okay. So far, okay. I think the main thing you want to remember is this relative chain group. Okay, if this makes sense, then you can define the chain complex. After chain complex, you can define homology. Hey, by the way, Rayshawn, where is this week's study group? Not posted yet. Oh, I did. Okay, okay. Because this week got midterm, the student to meet. Huh? Wednesday. Yeah. And then another follow-up thing, actually, I forget to say last time was Rachel actually asked about this thing, right? About yeah. Actually, also on Monday's lecture 14, right? I add a few picture in to relate your delta complex and your original topological space. How do you see this one simplex here as a one simplex on torus? So where are this actual cycle happening? So you see they are called cycle because inside the topological space, it is really a cycle. It's a loop. And then what did Rachel do last time? Okay, so because we proved that when RP2, right? Okay, when RP2, H2 is Z2. So we also see this Z2 in the pi 1 case here, but the way we get this Z2 is coming from the free group presentation. Okay, C quotient of 1 C squared, but what is C here? So what's the pi 1 of RP2 here? We don't need to use Van Kempen, that advanced thing. So in this delta complex here, right, you should pick up your loops. Okay, so how to pick up your loops? So you need to fix a base point first because pi 1 is about base point. So maybe you fix V, for example, then C is a loop because C is from V to V. And then another loop is not A, it's not B, you need to combine them. Okay, you can take, for example, AB inverse or BA inverse also can, up to you. Okay, then these two will form a basis of your pi 1. Okay, and then if you still remember, the two cell will tell you what loops are contractible. Okay, so there are two cells then, so there are two relations. Okay, and then these two relations using this generator here will reduce to C squared. And this is how you get Z2. So you see in pi 1 it's C quotient by C2, but in homology when we compute it's C quotient by 2C. Okay, so this is like a abelianization. Okay. Any questions so far? I have an update last week, not already. with some beautiful picture also, right? So how do you see this AB inside your real projective space? Okay, so please check it out, lecture 14. Yeah, for the typeset, right? Please keep updating. Check is there update version from me. And then if I ask you to do the exercise, right, please do. I give you the whole semester to do it. So until the last week, you need to submit the proper one. That one will be for evaluation, no? And then will be for your revision also. Okay. I think so far, those who work in full is got Larry, got Eric so far only. Yeah, the rest, please fill it in. Okay. If you don't know how to fill in, you should come and ask me. Either I also don't know how to fill, or either I know how to fill. You should come and ask me. Okay. Right. So far, so good. Okay. So maybe we can look at the relative cycle here. Okay, how does the relative cycle here looks like in Hn of x? Okay, how does the relative cycle here looks like? Okay. Okay, if you look at this chain, right? Okay, how does this relative cycle looks like? I mean, a trivial relative cycle. Okay? What is this popping up? Okay, how is it the relative cycle here looks like? I mean, the trivial one. It must be a kernel of a boundary map. Kernel of a boundary map. And then what's in the kernel? First of all, it could be a image coming from a previous boundary map. Okay. And then there's one more thing that helps you to make things zero, right? The quotient. Okay, so maybe you have some element in C. Okay, so there's some extra thing here. Previously, it's as a boundary. Okay, so if and only if it is a relative boundary. So here we define the relative boundary to be something coming from a higher degree plus something that come from the quotient, the thing that get quotient. Something from the denominator. Okay. So this is something in Cnx over Cna. Okay. Okay, so what we have defined here, you can understand it as a homology of x modulo A. Okay, so it's like we introduce a modular arithmetic into a homology. Okay, homology of x modulo A. Okay, so intuitively, we have tried to put modular arithmetic into here. Okay, Hn x. Later, you will see more example why this makes sense. So this is called homology of x modulo A. Okay. Okay, there's one example maybe worth to share here. Let's see this example. See this example here. So let x be a singular simplex, degree n. And there's some special thing here is the image of this sigma, right? Intersecting the complement of A is non-empty. Okay, this is a special set here. So it just says that S is the set of all singular simplex whose image is not completely contained in T. Okay, so if you look at this picture here, so this is delta 2, and this is your x, and this is your a. And these two elements here will be included in x, but this is not. Anyway, let me see. So image and real interchange. Okay, so these two here is in x, but this is not in x. Okay, so far so good. Wait, let me see. 讲错了哈。Whose image is not completely okay? Good. 外面两个 these two are in x. Okay, so 写一下，这样好。So this guy here is in x. This guy is not in x. Okay, whose image is not completely contained in x. Then what's this here? Then we can check that this map is isomorphism. So what's this map here? Well, what is this as? Okay, so this here we're just trying to say that this Cn here is a free abelian group. Okay, why is it a free abelian group? We try to say that there's an isomorphism between Cnxa to this. Is there something wrong here? Things are not wrong here. Okay. So okay. So here is a equivalent class because here is Cnx over Cna, but here is an element that that generated by this sigma I. So how many sigma I here will depend how many x. Okay. Yeah, this s here actually is the s we refer here. Maybe should I put s like this? How many x inside here? Or I think cannot be how many, right? Because some of them could be scalar of each other. So just put a number that depend on s. Okay. But the point here is the boundary map does not necessarily bring this subgroup of Cnx to the corresponding subgroup of Cn minus 1x. Okay, so this is the point here. So anyone understand what this says? The boundary map does not necessarily bring this subgroup of Cnx to the corresponding subgroup of Cn minus 1. Okay, Cn minus 1x is a map that defined on delta n minus 1. Okay, and then what does the boundary map do to this subgroup? Why is it true? Suddenly cannot recall. Why is it not true? Let me think. So it is usually better. Why is it not true? I suddenly forgot. However, the boundary map does not necessarily take this subgroup of. So meaning this x of something to do with this x here. Why you cannot bring it to something in x? 一般会发生什么事情呢？我想有什么事情？所以 boundary 不在里面，不在哪里里面？我去 A 里面就不见掉了，但是它还是在 X 里面哦 ，still in X right？ boundary 做 boundary map does not necessarily take the subgroup Cnx to a corresponding subgroup. Oh, okay. I think is if you are start from this X, right? If you go to the next level, one of them might be going inside, completely staying inside A already. You hear what I say? So supposingly you want to have the boundary map such that this property of X that hold true, right? Always. Such that the image of this sigma and the complement of A is non-empty. But if you look at this element here, if you apply the boundary map, then there will be a part of dn minus 1 here. This is 2, right? So there's a one simplex here completely staying inside A already. So you are not in the S restricted to delta n minus 1. Does it make sense? So this subgroup will not be preserved. This subgroup will not be preserved under the boundary map. That makes sense? Continue. The boundary map does not necessarily take this subgroup of Cnx to the corresponding subgroup. 所以它 corresponding 的 Cn minus 1也是这个 definition， 只是把 n 变成 n minus 1罢了。但是如果你看这个 element 的话 if you look at this element, if you apply boundary map to it, then the boundary is like 1, 2, 3, right? But the third one would not stay inside the corresponding subgroup X because this one will stay completely inside it. Okay. Make sense? Okay. Okay. How about look at some examples? Okay, let's look at some examples here. Very interesting examples. Look at this relative homology here. Okay. Good. 非常好. Okay, 非常好. Like, let's look at this cylinder, sorry. Okay, let's look at cylinder. 在 calculus 1也在画 cylinder， 在这里也在画 cylinder。Understood. Okay, cylinder. So let's look at subspace here. Okay, so this is our X. And then what subspace we want to take here? Take the bottom circle. Let's take the bottom circle. Okay, so we want to ask what is H1 of X. Okay, what's this one? Okay, so right. So let's construct an element inside here. Okay, let's construct an element inside here. Let's call it sigma L1 to X. Okay, so let's see how we construct this. So maybe I write down this parameterization. You tell me what is it. Okay, you guess where is it? Where is it sigma? Okay, where is the sigma? Okay, write down a parameterization for you. So where's the sigma here? Where's the sigma? Maybe I should put the 3D for you. Okay, the top circle, right? Okay, the top circle is the sigma that I wanted now. So this is the sigma I want. So sigma is a closed curve in X, okay? Because we have the endpoint to be the same. So how about the boundary? The boundary will vanish. Okay, the boundary of vanish. In particular, boundary of sigma E1 minus sigma E2, E0, which is 0. So therefore, sigma lies inside Z1 of X. Okay, and Z1 of X, can I write like this or not? Z1 of XA. Okay, we view XZ1X as a coset here. Okay, and it represents a non-trivial class in H1X. Okay, so what is Z1? Z1 is the kernel, the set of cycle. I think we define it right. Kernel of Dn. Boundary, yeah, boundary is Bn. Okay, but the claim here is, however, the image of sigma in H1 XA vanishes. Okay, it is a valid element in H1A, H1X, but in this relative homology here, this one vanish. So how do we prove that? So we want to show that it is a boundary of something, or at least something that we get quotient of. Okay, but how do we do this? So let's consider this two things here. So consider the two chain. So let's call it the tau 1 and tau 2. Okay, so what's tau 1, tau 2 here? Need to draw it up. All right, so here is the two simplex picture here. So two simplex like this. 0, 1, 2, like that. Okay, delta 2. So how do I map it? Tau 1 and tau 2 here. Well, let's the above be the sigma, and then bottom we still have a relative subspace, right? Call it alpha. Okay, and then why do we have a beta here? Let's call the vertical part beta. Okay. Beta. These two have to get identified anyways, right? Later. Okay, and then let's draw some gamma so that we can glue our simplex. Okay, so how do we glue our simplex? Huh? Let's see. Okay, so to glue our simplex, I'll tell you how I glue this side here. So I will put D2, so let's label it. So here is 0, here is 2, here is 1, and here is 0, here is 1, here is 2. Okay, so far so good. I think this is enough, right, to tell you the gluing. Enough, enough so far. Enough, right? 0 where, 1 where, 2 where, and then that's good. Okay. So this picture in the cylinder form should look something like this. And then where's our C here? If I'm not wrong, maybe you can check. Our C should looks like this. Okay, C should look like this. Okay, because this is key. Okay, so far. All right. So let's compute something. So let's look at some magical computation. So let's compute what is the partial on D1, D2. Okay, what's this map here? So partial is linear. So you do partial D1 plus partial D2. So partial tau 1 is like you remove one vertex, remove two vertex, remove second vertex, and remove the third vertex, right? Okay. So then should I write it like in this form here? So delta 1 restrict to V0, V1, V2, and then throw away V1 like that. Okay, and then minus delta 1 restrict to V0, V1, and then V2 like that, right? And then plus tau 1 restrict to V1, V2, throw away V2 like that. Okay. Can so far? Okay. So then what's the first one? Okay, if you throw away V0, actually what you get is this part, right? So this part, tau 1 of throw away V0, V1. So let's just write V1, V2 here. Okay. Okay, okay, huh? So okay, quite easy. Sigma minus beta plus gamma, and then if you do the other way for D2, tau 2, we get beta minus gamma plus alpha. So in the end, we have sigma plus alpha. Okay, with the alpha in C1. Okay, but what this says is, so sigma is actually in the boundary of XA. Okay, because we write sigma as an image of some delta, some 2 simplex plus something extra, but this extra thing I will gonna quotient it. Okay. So actually sigma is in the boundary of XA, and thus the class that represented by sigma is actually in H1 of XA, which is equal to Z1 of XA, throw away B1 of XA. Does it make sense? Question? Any question? Okay, if it is not relative, then this is not a boundary because it is sigma plus alpha. So it is the top circle plus the bottom circle. But now you take away the bottom circle already, then you become a boundary. Okay? Yeah. So if you look at the topological space, how should you think about it? You take away the bottom, you kind of like squeeze this bottom circle to a point. Then the top one obviously contractible, this become a cone already. Yeah. Does it make sense? So it won't be a non-trivial cycle. So it's like a modulo this circle. So I kind of squeeze this circle to a point, and then the top circle also not a circle anymore. It's a contractible. Oops. Okay, makes sense? Right, the cone it is contractible. Happy? Okay, ma. Question or question? Okay, so why do we need tau 1 and tau 2? Actually, that is the two cell that connect the two circle. So you need to at least have two, right? Because you want to make the square into delta complex. Okay, you at least need to have these two. Okay, I put another example inside the notes, which you can see later. Okay, next proposition. Any continuous map sigma from delta n to x with sigma of delta partial of delta n living inside A will define a cycle, okay, in the chain complex, relative chain complex, okay. Does this make sense? This should be obvious, but do you understand what it says? So if you have a continuous map such that this sigma acting on the boundary of this delta n here live inside A, then this sigma will define a cycle in the chain complex of C. So cycles means what? So we want to show that this sigma here will live inside the Zn. Okay, so why is it living in Zn? So to live in Zn meaning you want to show that boundary of n of sigma is 0. Okay. This is what you want to prove. But why is this true? If you write it out, this is sum of I with 0 up to n of -1 to the j, sigma restrict to various j. Okay, but what did we say about this thing? This is living in A. The image of this, wait, not the image of this, I'll say, if you have sigma, restrict on this whole thing here, will live inside A. Okay, so this is a map from partial del n or del n minus 1 to A. Okay, this is a map from partial del n minus 1 to A. But then what is Cn minus 1 xa? Okay, but then this is a guy in Cn minus 1 of x quotient out by Cn in A, which is 0 in this space here. Okay. Becomes 0 because it's something living inside the denominator. Okay, does it make sense? So this part here is by assumption. Okay, any questions so far? Seems like we did nothing, but it's not really significant, but very important. Okay, if you have a continuous map that restrict to the boundary is living inside A, then if you check the differential map on sigma, is just a sigma on the restricted boundary. Okay, but this is a map into A, but we are quotienting up A. Okay, so this is a 0 map. Okay, so far so good. Any question so far? No question. Because we only have 5 minutes left, so we'll brief what we're gonna do on Wednesday, which is diagram chess. Okay, this is a very new technique you never see before. For sure, your high school also never see it before. Your high school teacher also don't know it, so you must come and learn. Okay, diagram chess. So next Wednesday quiz will be on checking map on homology. Make sure you learn that. Will be a test on that. Okay, how a map on topological space induce a map on homology. Okay, we will prove it in the quiz. Yes, so make sure you try and revise it before Wednesday. Okay, so let's brief what we're gonna do on Wednesday first, and then I will do diagram chasing. Okay, so first, what we get is a short exact sequence of Chern complex. This is something that we touched on just now. Is saying that you have a short exact sequence of ABC, but ABC itself is a Chern complex. Themselves are Chern complex. So you should see like horizontal line. Yeah, that picture. So where is it? I included. Yeah, this picture here. Okay. Okay, ABC along is a short exact sequence, but ABC is themselves are Chern complexes. Okay, so it's infinite on one strip. Yeah, but there are only 5 turns in the other strip. Okay, this is what we call a short exact sequence of Chern complex, XEX. Okay, just now short exact sequence is just 5 terms, right? But now 5 terms get repeated. Okay, this is what we call a short exact sequence of Chern complex. Don't ask me why is it not called a Chern complexes of short exact sequence. Not sure. Maybe you can think about it. Okay. Then the first thing we're going to prove is what we're going to say just now. We want to prove that there's a connecting lemma here. Okay, between the Hn and Hn minus 1, Hn of C and Hn minus 1 of A. Okay, so you can see that C is the terminal. Okay, we now link back to the start and then repeat like a snake. And sometimes we call this a snake lemma. Yeah. And then we're going to prove that this connecting homomorphism is natural. Okay, so what does it mean by natural? This means that if there's a commutative diagram, okay, there's a Chern map between two SES. Can you imagine this? Short exact sequence of complexes, there's a Chern complex. So you get this waffle, right? Get a second piece of waffle. And then there's a map between these two waffles. Okay, can you imagine? So you get this waffle and then take another waffle, and then there's a map between these two waffles. Okay, if you have this map between these two map waffles, then these two induce a connecting homomorphism, right? But then the two connecting homomorphism will commute. Okay, commute. Very nice commutativity, yeah. Okay. And then we have this long exact sequence of. Then as a result, we will have long exact sequence. Okay, others exactness is easy to check. Then plus the connecting homomorphism, we have this nice long exact sequence. And then moreover, you also have this naturality on this long exact sequence. So if you have map between two waffle again, then two long exact sequence also have these commutativity diagram going on. You also can have induced map between long exact sequence, and then they commute also. Very nice, huh? Okay, so that's what I say. Max is about connection. You have to make connection. If you have a map between two things, we must have some connection. Okay, this is a nice part about algebra. And then we can do it for triple of topological space. Okay, just now we do it for pairs, right? So we can apply it for triple actually. Okay, if it is pair, then B is empty. You can take B is empty. But now we can do it for pairs. So triple. So triple is just subspace B in A in X. And then what is the map between triples here? You want F of A inside A prime, F of B inside B prime. And then if we have a triple here, then we have a connecting map between Hnxa to Hn minus 1A. So this is like a relative version to what we had just now. A relative version for short as a sequence of Chern complex. So here is so do you recognize what's the short as a sequence we're looking at here? What is the short exact sequence of complex we're looking at here? You recognize if I let you see this? Can you guess? Do I have it? So this is the short exact sequence we're looking for. AB, XB, and XA. Is it true or not? This is a bit like the second or third isomorphism theorem. A over B to X over B. So okay, let me write it here. So this is a bit like the second or third isomorphism theorem. I think second. So X over A will be equals to like A over X over B over B over A. Like that. Okay. Second one, I guess. Third one for the intersection, right? Okay. But then this is repeating what we had just now, but in the relative form. Okay. So the main part is the previous part, the diagram chess, and then this part is for relative version. Okay, relative version, you just need to describe what happened after you take the quotient, why things still hold true. Okay. Any ideas so far? Okay, so we take a waffle, get an arrow, and then induce a map on homology, and then homology also commute the chamber. This is the whole idea we're gonna do. Okay, your question? Okay, so this technique is very new. I saw diagram chase. Diagram chase. New name for your orientation game, huh? Diagram chase. Let's do diagram chase. Okay. 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 See you on Wednesday, and then we will discuss the results. Discuss it. Ask your friend to come. 哪里的？Actually 没有这样招来，其实。
啊，